Welcome. Today we are dissecting Heapsort, a cornerstone of computer science. We will explore how it achieves optimal efficiency through recursive structures, the heap data structure, and clever memory management. Before we build the heap, we must understand the rules. In comparison-based sorting, we strictly compare pairs. Mathematically, it is impossible to sort distinct elements faster than n log n in the worst case. This is our universal speed limit.
We often compare three giants. Merge sort is stable but eats auxiliary memory. Quicksort is blazing fast but requires stack space for recursion. Heapsort occupies a unique niche. It combines the reliability of merge sort with strict O of 1 space efficiency.
The magic of Heapsort lies in the binary heap. It is a complete binary tree, meaning it is packed tight. Crucially, we do not use pointers or references. We map the entire tree structure directly onto a flat array using simple math.
Because we have no pointers, we calculate navigation with arithmetic. If you are at index I, your left child is at 2i plus 1. Your right child is at 2i plus 2. This allows us to traverse the tree structure with zero memory overhead.
There are two flavors of heaps. In a max heap, every parent is larger than its children, ensuring the largest element sits at the root. We use this for ascending sort. A min-heap is the exact inverse, keeping the smallest element at the top. When the order is broken, we run a procedure called Heapify. First, we identify if a child is larger than the parent. If so, we swap them. Then, we recursively check the affected subtree to ensure the change didn't break order further down. Standard recursion uses stack memory. To keep Heapsort strictly O of 1 space, we use tail call optimization. We convert the recursion into a simple while loop. This ensures our memory footprint remains constant, no matter how huge the dataset becomes.
How do we turn a random array into a heap? Williams originally proposed inserting elements one by one, costing n log n. However, Floyd discovered a smarter, bottom-up approach that runs in linear O of n time.
Floyd's genius relies on the geometry of the tree. The cost of building a heap is the sum of the heights of the nodes. Since half are leaves with height 0, the mathematical series converges to linear, O of n, rather than log linear. Once the heap is built, sorting is mechanical. 1. Swap the maximum value at the root with the last element. 2. Shrink the valid heap area. 3. Sift the new root down to restore order. We repeat this until the heap is empty.
Here is a pro-level optimization called the bounce. Standard sorting checks parent versus child at every step, but usually the element sinks all the way to the bottom, so we skip the checks, dive straight to the leaves, and then bounce back up a little if needed.
Let's summarize the metrics. Heapsort is rock solid. It guarantees n log n time in the worst case. It requires strictly constant O of 1 auxiliary memory. However, it is unstable. It changes the relative order of equal elements.
Why don't we use Heapsort for everything? Cache locality. Quicksort reads memory sequentially. Heapsort jumps around the array in powers of 2, causing cache misses. This makes it slower in practice, despite the theoretical safety.
Heapsort is the unsung hero of modern systems. Algorithms like introsort start with quicksort for speed, but switch to Heapsort if things go wrong. It provides the mathematical guarantee that keeps our systems stable and predictable.